Spot the Bug? Welcome to another one of our Spot the Bug sessions. Today we're going to be talking about bugs in your use of Pandas or NumPy. And although not every single thing that we look at will be a bug in the sense that it will be a syntax error or cause some other very visible error in your code, we'll be talking about things which include disfluencies or approaches that will get you in trouble later with a goal to be able to improve our use of these tools by understanding why these disfluencies are disfluencies, why these errors occur, how we can use tools like Pandas and NumPy more effectively. We have a lot to cover, and so why don't we jump right into it? I'll share my screen with you. Let's get started with the very first question. This question is titled, More Index, More Problems? In this question, we'll talk about what the Pandas index is, how it can be used, and what the general thrust of Pandas code is. That is to say, when you're using Pandas, our goal is not to solve one small, narrow problem, but to solve multiple simultaneous problems using the index as the axis against which we're able to scale up the number of solutions that we have for a given problem. We'll talk about what the index is all about. We'll talk about this general approach and thinking that we employ when we're using Pandas. We'll talk about the multi-index and why the multi-index is related to this, and how multi-indices can help us solve real problems. However, there are a couple of things that we won't have an opportunity to talk about. Namely, we won't be able to talk about where the multi-index shows up in practice, how we can use multi-indices more effectively. We won't have an opportunity to talk about the limitations or the restrictions in the use of the multi-index, and we won't have an opportunity to talk about some of the more sophisticated ways that we might push computation into the index, or how we might write code to be amenable to FastPass that may later be added to Pandas, how we can write code that's not fast just today, but fast as the library around us evolves. With that said, why don't I show you the sample data that we'll be using for our very first Spot the Bug. Here, we're going to imagine that we have an empire of hamburger restaurants, and we have some information from these hamburger restaurants. We have their monthly sales data. And so if we take a look at our monthly sales data, we can see for each one of our store locations, for each of the items that we sell in that store, we have some quantity of items that are sold. So for one location like New York, we sold 67,000 hamburgers in this monthly sales data. If we look at the unique stores, we can see we have locations in New York, San Francisco, and Chicago. If we look at the items, we can see we're a very simple restaurant selling only hamburgers, milkshakes, and French fries. And if we look at another data set, forecasting, we can see that we can take this monthly averages data, and given some forecasts, we might be able to predict how much sales we might have through some mechanism. We've said in Q1, our total sales will dip by 3%, and then it'll pick up later in the year, and then it'll dip again in Q4. Perhaps people like to eat hamburgers during those summer months. Whatever the case may be, we can use these two data sets together in order to answer a question like, given my monthly averages, monthly sales data for my locations, what would my projected sales be for these 4 quarters, for every item, for every restaurant? Here we have our program that's going to take a look at a small, narrow question. We're going to look at our New York hamburger sales, our San Francisco hamburger sales, and our Chicago hamburger sales. And we're going to try to compute that against our growth. And so we'll compute the New York hamburgers, the San Francisco hamburgers, and the Chicago hamburger sales against our growth. And my question for you is, can you spot the bug? If you took a look at this code and you said the bug might be in the input data, well, I wouldn't quite do that to you. The bug is not in the input data. If you look at the code and you said, oh, the bug is in our masking, well, the masking all works. These are, in fact, our New York, San Francisco, and Chicago hamburgers. If you took a look at the code and you said, oh, maybe it's in the multiplication, well, in fact, the multiplication works perfectly, and we can actually perform this operation. But if you took a look at the code and said, there's not a bug, but there is an incorrectness in the way in which you're approaching this problem. It seems a little bit off that you'd have these 3 variables that look almost identical in their computation, New York, San Francisco, Chicago, and it seems as though if you wanted to do this more robustly, you might want to make use of some sort of looping Or if you want to do this more robustly in Pandas, you would have Pandas answer not the one small narrow question, but every question simultaneously. And in fact, that is the very first bug, even though this is something more of a disfluency that we're going to talk about. It is the case that when we're using Pandas, our goal is to make use of a specialized vocabulary, what you might call a jargon. It's not regular, everyday, common English, but it is a specialized vocabulary for doing data transformation, manipulation, for doing analysis problems. And as long as people are broadly aware of what that jargon is and they're familiar with that jargon, we can tersely and directly express very complex questions about our data, very complex transformations of our data. And in Pandas, our goal is not to solve one tiny narrow problem. Give me the forecast for this item, for this location, but to make use of the tool to solve multiple problems simultaneously. In fact, in some cases, we can solve every possible problem that the data presents to us and then project down to the question our end user actually asked us to solve. And the reason that we might do this is if we think about where the churn in our code tends to be, it's often the case that the churn is at the seams, it's at the boundaries. It's at the boundaries between the work that you do and the work that somebody else does. Somebody came to you with the business problem. I have this forecasting data, I have this monthly sales data, and I want you to use that together to tell me what my monthly sales are going to look like in these 3 quarters. And using that information, you solve one narrow problem for one item for one location. And they come back to you and say, well, what about for every item? What about for every location? What about subject to this additional criteria, maybe the scaling factor? And your goal, in order to reduce that churn in your code, is to solve all of the possible problems that they might bring to you all at once, so that when they come back to you with a small amendment to the problem, do only hamburgers and French fries, but don't include milkshakes, you can project your solution down to what it is they're asking for. And that projection itself should be very, very simple. It should be some sort of filtering or some sort of selection of columns or some sort of very minor transformation. And as a consequence, after having done quite a little bit of upfront work, you would have something which can solve not just the one problem that's sitting in front of you, but every subsequent problem related to that data set that comes up later. And you can solve it very quickly without having to do a lot of work at the core of your transformation. That's what we might call very fluent and very robust use of Pandas. Let's see how we might do that with this particular data. Here we have, again, our monthly sales data for each store and each item. And you can see I've set this up with a multi-index. I have the store and the item, and we have our forecasting data. And presumably, what we're looking for is what the monthly average is going to be in each one of these quarters. Generally, when we use Pandas, the easiest way for us to use it is to first solve one small, narrow problem. And so let's solve one very narrow problem. Let's look at just New York, just for hamburgers, and just Q1. If we take the value for New York and hamburgers and just Q1, you can see this is what our Q1 monthly average is going to be for hamburgers, 65,000. And what we can do is we can step up the generality or the scope of the problem that we solve without changing the code that we write. And so this line of code is going to get only barely more complicated, and yet the problem that we solve is going to get significantly broader. Let's solve a broader problem. Instead of New York for hamburgers, let's solve every item that was in the New York location for that one particular quarter. And you can see it's basically the same code, we just changed the filter. And here you can see index alignment in Pandas. Pandas said, you wanted me to do not one multiplication, but multiple multiplications. I'll do them all together, and I'll give you a series object back. We can keep going. Instead of just one location, what if we try and solve this problem for every location? So we eliminate our filtering, and you can see with just the same code, modulo some jargon, this is no longer saying one exact value multiplied by another exact value. This is saying all of these values for New York, the item, San Francisco, the item, Chicago, the item, multiplied against the forecast. Well, there we go. And finally, if we wanted to solve the broadest problem, not one particular location with one particular item against one particular quarter, or every location, every item against one quarter? What about every location, every item against every quarter? What you can think is the key to this problem is that indexing. And in that indexing, we have multiple layers. One of those layers is the store, the next layer is the item. Well, in our result data, it stands to reason that we want to have one more layer to that index, one more level to that index, namely the date, which quarter, which financial quarter we're talking about. Well, in order to make this work in Pandas, we need to make use of the multi-index. What we'll do is we'll construct a multi-index, and we'll construct that multi-index by taking the existing index that we have on the monthly sales, computing a Cartesian product of that against the index that we have on the forecast. This resulting index will look exactly like what we can imagine the output to look like. New York, look, item, quarter, Chicago, item, quarter, San Francisco, item, quarter. It looks good. And we can take each one of the data sets and re-index them. And so here you can see we take our forecasting data and re-index it. This just means some sort of repetition where that quarter indicates what that item is, and the store and the item are just some axis of repetition. Well, we can just multiply times this re-index structure, and then Pandas index alignment will pick up, and you can see we have solved not one small narrow problem, but every possible problem. And then somebody will come to us and say, well, I only care about the first 2 quarters of the year. I only care about these particular items. I want you to sum these. And from there, it's just very simple transformations, projections, a minimum of work that you have to do to service that next variation of the question that you're looking at. So what do we do with this information? What do we do about this? Well, whenever we use Pandas, we should pay very close attention. We should be very careful with what our indexing is. The indexing is probably the most interesting thing about a Pandas series or a Pandas data frame. We should also be broadly very careful about whether we're working with series data or working at data frame data, whether we're working with single column structures or multi-column structures. And this is because this will affect our index alignment, as we may see later. The index, we can think, should be either the primary criteria that we're using to filter the data set, or the axis across which we are performing repeated computations, things where we'd otherwise loop. Now, sometimes it can serve both of these tasks, but these are the 2 characteristics for how we might choose an appropriate index. The proper use of the index tends to lead to being able to solve not one specific problem, but multiple problems simultaneously. And good use of Pandas is typically use wherein we stay within that index. We're doing operations where we're not just resetting index all the time, but we're making use of that index to solve something useful. And we often find that a good amount of our code is working within that index, doing sort of re-indexing or constructing new surrogate indices, whatever the case may be. Some operation within that index, which then leads to the underlying transformation or analysis. Our next question is titled, how do I go row by row? And in this question, we'll talk about things like restricted computation domains. We'll talk about the apply method on Pandas data frames and series. We'll talk about the items and iteritems methods on data frames and series. And we'll talk about why it is that we might want to avoid them with one important qualification. Why it is that we want to avoid doing operations on the scale of the data. Why it is that we want to avoid pure Python, when it's not 1 or 2 loops, but it's 10,000 or 1,000,000 loops. It's 1 per row, not necessarily 1 per column. We'll talk about what a restricted computation domain is and why this terminology is quite useful for us to understand why it is that NumPy and Pandas operate the way they do and why it is that our NumPy and Pandas code look the way they do. And there are a couple of things that we won't have an opportunity to talk about. We won't have an opportunity to talk about why group by apply is slow. It's a very different reason than why .apply is slow. And we won't have an opportunity to talk about how we might push computations into the restricted computation domain. This is a considerable amount of the difficulty of Pandas and NumPy is trying to figure out how you can adequately encode your computations in a way which Pandas and NumPy can make them fast, in a way where they stay within that domain. Let's take a look at how we'd solve this problem, leaning into the Pandas API. Here, we can see we construct a multi-index from the price and the locations, and we merely do a multiplication. And there's still some looping here. There's still some code behind the scenes that is going to do some looping for each one of the locations for each one of the items. But it's not looping at the pure Python level. It's not looping in a way where we're exposed to that, and we have the ability to do something with that looping, to interrupt it or to interleave other operations with that looping. So what does this tell us? Well, it turns out that the use of pure Python is quite inefficient. Generally, we should reserve pure Python for things which we might consider program structuring, things which occur at the human level. And we should defer to tools like NumPy and Pandas for anything that is purely computational in nature. Because in pure Python, every value is an object. There is significant overhead to every value that you might have. There is what you might call boxing of all of these types, and there is no control whatsoever over the memory layout or the total memory use of these values. For example, if you look at a value like the number 0 in pure Python takes 24 bytes. But if you think about it, for a 64-bit integer, that would be 8 bytes. So 16 of these bytes are completely wasted by the overhead. And if you thought I have a very large data set with just numbers in it, I'm wasting 2/3 of my data on just the overhead required by the Python interpreter. Now, if we grow this number a little bit, if we look at 2 to the 8th, 2 to the 16th, we can kind of see that overhead is fixed, and we can see a little bit about the nature of how the underlying data itself is being stored. And so it's the case that if these numbers were very large and there were very few of them, well, then the overhead wouldn't be that large in reference to the number itself. But if you think about it, it's very often that we're working with numbers that can be fit into an IEEE 754 double precision floating point type or into an Int64. And when we do that, we're paying a lot for the overhead in pure Python. If we were to imagine that we had, say, a tuple of 3 values representing one record, here this tuple is 64 bytes in size, but the underlying data that it contains is significantly smaller. Each one of these could be stored in a 1-byte integer, in which case we're wasting 61 bytes of data, or if we wanted to use a default 8-byte integer, we can still think that we're wasting 40 bytes of overhead for the purposes of storing this data. And so there's got to be something that we can do to reduce all of this overhead so that we can work with larger data sets. Because if we could eliminate this overhead, imagine we could more than double the size of the largest data set they were able to work with. And that's a very good bargain. The other thing that we need to consider is, if we have, for example, a list of these floating point values, and we look at where these floating point values are located in memory, where they've been allocated, well, it turns out that they are not allocated contiguously. They're not next to each other. And in fact, we may not even be able to guess where one of these values is based off of knowledge of where the others are. If you look at these memory locations, these are, of course, the unique identifiers for these objects, which in CPython correspond directly to the pointer values for where these objects are located. You can see they're not stored in order. They're not stored next to each other. You couldn't guess what one of these values is given the other ones, which means we do know that when our CPU is performing operations, there's a lot of ways in which we can do bulk loads. Instead of loading one particular value, we can load large sets of values. And we may even know that by default, we are not loading 1 byte at a time. We're loading larger structures, pages at a time. Well, you can think that if you were to perform a computation on this list of Python floats, what you'd have to do is you'd have to do multiple memory loads. And you might not even be able to predict ahead of time which memory loads you would need, where those memory loads would have to be. You'd have to do a lot of what we might call pointer chasing. And as a result of that, this is just going to be slow. We're going to have to do a lot of interaction between the CPU and main memory, and we're not going to get any of the benefits of co-locating this data, of packing it really close so we can do everything at once, do one load, and then given that one load, do some sort of aggregated operation. None of those benefits that our modern CPU give us will be available to us as a consequence of this. Similarly, if we take a look at this list contains 3 numbers. One's an integer, one's a floating point value, and one's a complex value. We can think that if we wanted to sum these up, it's completely valid to sum these up in pure Python. And in fact, Python gives us exactly the answer we expect. But in order to do that, it needs to know each step along the way of this sum Well, what am I summing up? Am I summing up integers or am I summing up floats? Python dynamically dispatches these operations. Python waits until it looks at the value it's about to add to the total before it determines what the operation is going to be. Which means if it's not just 3 numeric values, but 10 million numeric values, of which all but 1 is an integer and 1 is a float, every step along the way, Python needs to use software to determine, is this an integer? Is this a float? Do I continue with my integer addition or multiplication? Do I continue with my float integer addition or multiplication? And there's a lot of choices that have to be made on the scope or scale of the data. There's a lot of software that has to run for something which might otherwise be a purely hardware operation, summing a bunch of integers or summing a bunch of floats. And because Python doesn't know ahead of time that, for example, this list is going to contain only integers or only floats, it's not able to optimize this in any way. You can't say, oh, this is 10 million values and they're all integers. I'll just use some hardware-supported integer addition and I'll skip any sort of software layer in between that is dynamically dispatched, dynamically deciding what that next operation is going to be, an integer add, a float add, or a complex add. And if you think about it, for Python integers, because they automatically promote, there is necessarily some software support for these simple operations, because once the value gets too large to fit into a 64-bit integer, it has to figure out, oh, this is too large to fit into a 64-bit integer, maybe I need to do something else. And in fact, it's not even a 64-bit integer. If you look at how Python integers are implemented, they're actually implemented as signed in 32 digits. So this problem props up even sooner than you might expect. But nevertheless, what you can think is any step along the way, it's not able to say, oh, let the hardware do its typical overflow, underflow operation. There has to be some software intermediating that, and this is going to add to some slowness. In general, executing Python bytecode is relatively slow. It is relatively slow compared to executing single assembly language instructions. It is definitely slow compared to executing large-scale assembly instructions, things like your AVX instructions, anything that works on vectors. Python function calls historically have also been relatively slow. For one Python function call, there are more than 5 C stack frames, up to 7 C stack frames that need to be incurred as a cost before you're able to execute that Python function. And so Python function calls are one thing which oftentimes people have tried to minimize in their code. Instead of calling a function in a tight loop if that function gives the same value, they'll pull that out and see a dramatic speed up. As a consequence of these, what we find is we're not able to get the performance that we want for purely computational work out of pure Python. Here's a simple example that shows you the idea of the restricted computation domain. Because the idea of the restricted computation domain is, because pure Python is so general, and because pure Python in that generality doesn't give us the speed that we want, we will carve out a part of our program, a domain within that program in which we will do only computation. And we'll keep our computation within that domain. As long as we keep it within that domain, we've created a boundary behind which we are free to choose other alternate implementations, such as implementation in pure C, implementation in pure assembly, implementation in Fortran. And we can get all of the performance that we lose from pure Python back, but only as long as we push all of our computation into that domain and we stay within that domain. And I like this phraseology of the restricted computation domain because it directly leads to what is otherwise a somewhat perplexing result, but once we think about it in the right way, seems completely reasonable. Here, we have 2 lines of Python code that we're going to time. And these 2 lines of Python code create vectors of size 100,000. They create vectors of size 100,000 of random values from 0 to 1,000. Notice, this is a pure Python loop. We have the ability to interrupt this loop in our code. We have the ability to interleave operations with this loop. This loop is happening at that pure Python level. And when we run this code, you can see some timing. It takes about 1/4 of a second. That we say pure Python is relatively slow doesn't mean it's that slow. This is still reasonably fast for operations. And you can think if your data set doesn't grow larger than 100,000 elements, this may be fast enough already. Here, however, we take a look at the same operation within NumPy. And note, there is a loop somewhere to create each one of these 100,000 values. It's just not visible to you. It's somewhere within NumPy. Whether or not that loop is in pure Python code in NumPy or in the C layer in NumPy is something which is difficult for us to answer in general unless we take a look at the source code. But our idea behind NumPy is, it doesn't matter because NumPy is this impenetrable membrane. And as long as we're pushing the operation into NumPy, anything that's in a pure Python loop in NumPy today could be moved into a pure C loop or a pure Fortran loop without the code that we write ever noticing it. Now, in this case, we can definitely see that pure NumPy is doing something very different than pure Python. Here, this NumPy code is definitely faster. It's almost 100 times faster, or even more than 100 times faster than the pure Python code. And so, most likely, this random integer creation routine is written in C or assembly or Fortran or something that's not pure Python, which is why we're getting this speed back. Now, if we try and do a computational task, here we see a dot product, and that dot product is implemented as a pure Python loop using, again, our comprehension syntax and a lambda right here. And if we perform this operation, we can see it takes us about 1/100th of a second. If we perform the corresponding operation in NumPy, likely this has been implemented at the C layer because this is, again, significantly and dramatically faster. As long as we stay within pure NumPy, we have created this boundary behind which NumPy is free to implement as it pleases, and it can choose a better implementation, namely an implementation that focuses on performance, like one in assembly, C, Fortran, or whatever other language NumPy wants to re-implement in. However, if we try to cross the domain, if we write code that makes use of the Python data and the NumPy dot product, we can see how the timing lines out. And it's actually worse than if we had just stayed in the Python domain. And even worse than that, if we had taken that pure NumPy data and used our pure Python solution, and we crossed a boundary in the other direction, it's even worse than that. And as we look at these timings a couple times, you can see there's quite a bit of variability in these timings. But in general, we see a consistent pattern, namely, stay within the domain. If you stay within that pure Python domain, it's actually better than if you cross a domain. If you were to perform this operation in pure Python and pretend NumPy doesn't even exist, that is better than trying to use NumPy, but not pushing all of the computation into NumPy and crossing that domain. And it should make sense why. The idea of the restricted computation domain is we create some boundary layer, and that boundary layer allows us to re-implement things inside that boundary layer in a more efficient way. In the case of NumPy, this means working with raw machine-level types, so there's no more dynamic dispatch. Working with contiguous memory, so there's no more pointer chasing. Eliminating some of this software support, there's no more automatic promotion. And controlling memory usage and memory layout, so it's no longer all of this overhead. There's overhead for that NumPy container object, but there's not overhead for the individual items. As a consequence of all of these assumptions that we can make while we're inside that domain, what we're able to do is significantly increase our performance. But every time we transit the border of this domain, we have to move from one to the other. We have to take these boxed Python objects and unbox them. And the cost of that tends to be relatively high. If we're doing that on the scope of our computation, we are going to pay an enormous cost. And this is exactly what we see. With the restricted computation domain pattern, stay within the domain. Don't move back and forth between it because it's going to be worse than if you stayed within it in the first place. Here, we can take a look at what NumPy does. And again, what NumPy is doing is it's giving you a interpreted view of raw memory. So it's interpreting this raw memory to be in64s. It's interpreting this raw memory to be in64s for a block of memory at a particular location. If this memory block is very small, what you can think is the advantage that we get over pure Python is probably quite minimal because the pure Python routines are not that slow. And the cost of creating this domain and the overhead of the domain itself, the NumPy wrapper object, is going to be relatively high, corresponding to or in relation to the size of the data. But if this data itself is very large, 1,000 elements, 10,000 elements, 100,000 elements, 1,000,000 elements, then the cost of entering this domain and the cost of all the overhead of that domain is now minimized, and we can see asymptotically the total speed should prefer our NumPy approach. Here, we have a pandas series. And if we dig into a pandas series and look behind the scenes, we'll see a pandas array. And if we look behind that pandas array, we will typically find a NumPy and D array. So all of this reasoning fits both for our use of NumPy and our use of pandas, and also our use of tools like Xarray, although in the case of Xarray, the superficiality of the tool itself is quite obvious. It's pretty obvious when you're using Xarray that there's NumPy behind the scenes. In the case of pandas, that may not always be as obvious. For the most part, at least today, you have NumPy lurking behind the scenes. So what do we do about this? Well, whenever we're using NumPy or pandas, we want to avoid iterating in Python. Therefore, we want to avoid operations like .apply, which iterate with a user-defined function on every row of the data. We want to avoid operations like .items or .iteritems, which extract from your pandas data frame or series the elements so that you can operate on them in pure Python. But an important qualification is we want to avoid iterating on these on the scale of the data. Because here we have an example where we have 3 columns in a pandas data frame. And what I'm going to do is I'm going to iterate over the columns and perform some operation. I'm going to absolute value them, and I'm going to end up iterating 3 times. There's not really a big deal here because the pain of working with pure Python and the speed and the performance penalty that we get is not that high if we only have 3 loops. What would be a problem is if we did this on the scale of the data, 300,000 loops. And so what we can think is the important qualification when we want to use these tools, especially when we want to integrate them into a Python whole, is avoid iterating in pure Python on the scale of the data, but it's okay generally to iterate in pure Python on the scale of the structure. In the case of most data frames, which tend to be taller than they are wide, it is generally okay to iterate over the columns. After all, maybe there are only 3 of them. But you're going to get in trouble if you iterate over the rows. If there are 300,000 of them, you're definitely going to see that performance penalty. Additionally, what we want to do when we work with these structures is push computation into that NumPy or pandas layer using what you might call Fortran 90 style vectorized operations. You want to make sure that instead of doing that operation explicitly in pure Python, you're having some sort of looping done implicitly by telling NumPy, please go perform this operation, telling pandas, please go perform this operation, and letting it figure out how to perform that looping. And in general, you want to operate on the overall structure. You want to operate on that NumPy and D array as a whole, on that pandas data frame as a whole, not on the individual values, not on the individual rows. Although in the case of pandas on the individual columns, sometimes can be okay, as long as there are very few columns on the scope of what a human being can think about, 10 or 20, not on the scope of the data, 10 billion or 20 billion. If I want to show you a very quick example here, you can see I have a pandas data frame, and I'm going to use the .apply in order to square some of the values. I'll square every value that's greater than 0 and cube every value otherwise. And if I do that with .apply, you can see it takes me about a quarter of a second. If I do this with numpy.where, which will still loop, it's just that the looping is not visible to you, and thus it can be implemented differently, you will see a significant performance improvement of over a factor of 10. And these factor of 10, factor of 100 performance improvements that you see when you begin to use these tools appropriately, when you avoid looping on the scope of your data in pure Python, it is not unusual. It is absolutely not unusual to get a factor of 10, factor of 50, factor of 100 speed up, just because eliminating dynamic dispatch, removing all of the overhead of boxing, making data contiguous, working with machine-typed data, all of these can lead to significantly faster operations because there are operations which can be written to whatever the hardware is able to do fastest. In fact, there are even cases where you can dispatch this work to your GPU. And from the perspective of your pure Python code, you don't know. This is a domain which has a boundary around it. And you have no idea what's happening inside that domain. You only control from the outside to tell that domain, oh, please go do this computation. And it goes and figures out how it wants to do it best. Our next question is titled, Isn't this aggravating? And this question is all about understanding pandas group by. What are the group by operations? How can we make sense of them? How can we use them? Specifically, what's the difference between transforming, aggregating, applying, and filtering? But unfortunately, we won't have an opportunity to talk about other common Windows functions, rolling, expanding, or resample, or how we can efficiently perform group bys that might require computations on multiple columns, or why it is that group by apply is something that we want to avoid why it is that it is so slow. Let's take a look at some sample data related to our enterprise of hamburger restaurants. And here we can see some additional sales data. And in this sales data, we have specific dates, specific locations, and specific items, and the number of those items that were sold on that particular date. So 640 hamburgers sold on such and such date, 4,000 hamburgers sold on such and such date in some location. Here, we have some sample code. And in this sample code, we want to take this daily sales data. We want to perform some operations on it. We wanted to, for example, compute the sum of the sales per location, and that works perfectly fine. We want to do that per month, and that works perfectly fine. And finally, what we want to do is we want to figure out what percentage of the sales for that day added up to the sales per month, because we may have some monthly reporting requirement, report all of your sales for this month, and we want to say 1% of that monthly sales happened on the 31st, 1% happened on the first of the month, or maybe there was a bulk of the sales close to the middle of the month, maybe for some reason towards the middle of the month, everybody wanted to go get hamburgers. We might see some seasonality here as well. Without running that last block of code, can you spot the bug? If you said that in this code we did a .ag, and that .ag is going to give us an error, it's going to complain that we have to produce an aggregated value. You got it exactly right. And better yet, if you said the result of this operation is going to have the same indexing as the input, and thus, instead of using .ag, we want to use .transform, you are even more right. That's exactly what the nature of this bug is. Because if we go back to this example and we change the group by operation that we do here from .ag to .transform, we get exactly what we expect. You can see 7% of the sales happened on this particular day of the month, 3% of the sales for that total of that month happened on this particular day, and we can do some other things to eyeball this data. We can see, oh, how did this data line up for the first 2 days of the month, and you can see the first 2 days of the month sometimes start off strong, sometimes didn't start off that strong, or the last couple of days. And if we do that, we could also look at the cumulative sum for the last couple of days. So we should imagine for the last couple of days that cumulative sum should come up to unity, should come up to 100%. But the core of this is the use of group by transform. So what does this tell us? Group by is a very powerful tool, but it requires some knowledge of the Pandas jargon and it requires a little bit of mechanical sympathy with Pandas. I use this term very specifically, and the analogy is this. You don't have to be a mechanical engineer to be a good race car driver. You don't have to know the internals of Pandas or be a computer scientist to be able to use Pandas effectively, as long as you have some mechanical sympathy with the tool. If you generally understand what makes the tool work properly, then you can generally discover why it is the tool looks the way it does, why it is that certain things may be faster than others, or why it is that certain approaches may work and others may not. Speaking to group by, there are broadly 5 different things that you can do with group by. You can perform some sort of built-in operation, which is usually an aggregation, like a sum, a mean, or a median. You can perform a filtering using a user-defined function. Maybe the built-in computations are not sufficient for your use cases. You need a user-defined function, and you want to filter on it. Or you want to aggregate on that user-defined function. So you want to turn multiple rows into a single value, or you want to transform using a user-defined function. You want to turn multiple rows into multiple rows, or you want to perform some sort of arbitrary computation on groups with some user-defined function. Now, we're going to focus our attention on the last 3 of these, aggregate, transform, and apply, because this is where the most confusion comes up. And unless you really have a sense for why it is that 3 of these may exist the way they do, it may be kind of curious, why would we have these 3? For example, in similar data transformation tools like SQL, there is no aggregate, transform, apply, at least not in so many words. What we can think is, one of the differences between aggregate, transform, and apply is the relationship between what the input looks like and what the output looks like. In aggregate, you're taking n total rows of the original data frame, and you're reducing it down to 1 row per group. In transform, you're taking n total initial rows, and you're returning n total output rows. There is no change to the size of the data. In apply, you're taking n rows, and there's an arbitrary computation. It's not clear from, without knowing exactly how that computation works, what that relationship is. And immediately you can see why it is we'd want to split these up. If you were Pandas, and you said that memory allocation is one of the costliest things that we might do, therefore, I want to try to reduce the total number of memory allocations that I do. Well, aggregate makes a lot of sense. Because aggregate says, if I have n starting rows, and I know exactly how many groups there are, so maybe I do a scan of the data to figure out where the groups are, I can figure out exactly how much memory I need for the result. And I can pre-allocate all of it. If I have n rows and g groups, well, I just have to allocate g rows worth of data for my output. If I have a transform, it's even easier. I just have to pre-allocate a structure that's exactly the same size as the input. Even easier. If I have apply, I can't do that. Because apply doesn't say, oh, this will produce one row for each group or the exact same number of rows as were in the group. It's an arbitrary relationship. And this is part of the reason why apply is so slow. Instead of doing one bulk pre-allocation, it has to do multiple allocations because it doesn't know how big these structures are until it performs that computation. And then it's got to stitch those together. So it's got to do a bunch of small allocations. Then it has to copy everything back over into one allocation, and it has to stitch these together in an indexed aligned fashion. Another way we could take a look at the distinction between aggregate, transform, and apply is what happens in each computation. Each computation operates on a group. So if that group has n rows, aggregate takes that entire group and gives you a scalar value. That's what the error was saying. My computation was supposed to give a scalar value, but it didn't. So aggregate is all about operations where you have n rows coming into the user-defined function and one row coming out or one value coming out. Transform is all about operations where you have n rows coming in and n rows being spit out. And again, apply, anything goes. The result can have any number of rows. Therefore, if you think about it, the aggregate operation will change the indexing of your input data. In the output will have indexing matching the grouping. So if you group by location and item, then your output will be indexed on location and item. Transform will preserve the indexing of your input data. So if your original input data is date, location, and item, and you group by location, the output will have date, location, and item. There will be no change to the indexing between your input and your output. Apply doesn't know ahead of time what the result is going to look like, and so what apply is going to do is it's going to concatenate the indexing of the grouping against whatever your user-defined function happened to give. So if you group by with apply by location and item, you'll see location and item on the outside, and then any layers of that index that your operation created. And so we can think of these three in terms of how they transform the index. Transform doesn't change the indexing at all. Aggregate will transform it exactly by the grouping criteria, and apply, anything goes. Why this may be useful is you often know what your output data is supposed to look like. And you know what your input data already looks like. And if you see that the output data looks exactly like the input data in terms of the indexing, that's a transform. If you see the output data doesn't look like the input data in terms of the indexing, well, it's probably an aggregate, in which case you're aggregating on those fields. And if there doesn't seem to be any clear relationship between the two of them, then it's probably an apply. There may be something more arbitrary that you need to do. An additional critical note: aggregate operates on each column of the data individually. Therefore, you cannot look at multiple columns when you're doing an aggregate. You cannot say, I'm going to aggregate these rows and I'm going to look at these two columns at the same time to produce the aggregated value. Transform is similar. It works on each column individually. It does have a fast path, but you're not allowed to assume that fast path. This is why that fast path is checked for the second run, not for the first one, just to avoid you making an assumption around it. Generally, we should only think about aggregate and transform as operating on the columns individually, whereas apply can operate on each group as a whole. So think about something like a weighted average. If you wanted to compute an average per group, that's easy. That's an aggregate because the average per group is just the sum of the group divided by the value. Actually, that would be a transform because you probably want to preserve what the underlying values are. So it depends on whether you want this to be a average per group or whether you want this to be a percentage contribution per group, whether it's going to be a transform or an aggregate. If you want to do something like a weighted average, you can think that a weighted average is going to involve the underlying value and the underlying weights in separate columns. You cannot do that in an apply or transform without some first performing some operation on that data frame to create a subordinate column, which you can then perform this operation on. You'll have to pre-compute a couple of steps of this, maybe multiply each of the raw values against the weighting, and then perform an average there. But if you need to do it all in one step, you'd have to use apply because apply is the only one that can see both columns at the same time. And so, if we take a look at our sales data, and if we remind ourselves what the index of this data looks like, you can see it's a multi-index with the date, the location, and the item. We can do some fancy aggregations. If we wanted to know what the monthly total sales per item would be, well, we know that the output is going to have a different index than the input. The monthly total is going to have the month and the total, irrespective of location. Well, I'm changing the indexing. It's probably an aggregate or an apply, and I probably want to use aggregate rather than apply, and thus this is just an aggregate with a sum. I can write this in a couple of different ways. Instead of doing .aggregate with a lambda, I can write an aggregate with the function name sum. I can do .ag with a sum. I can even do .ag with a passing in the function sum like this, or I can do this with the built-in sum. I don't really think there is a humongous difference between these. Obviously, this is the tersest, obviously this is the most direct, and obviously there's some amount of additional work that this avoids that the others don't avoid. I don't think that you're going to see a dramatic difference in the speed between these. All of them should just boil down to this in the end after just doing a little bit of dispatching. I do think that these might be a little bit clumsier, but in general, this is not where I would focus my attention. I'd focus my attention on the difference between aggregate and transform, and over time, learn how to write the shortest of these, but not really sweat the details in the interim. If I wanted to do something else, if I wanted to take this data and I wanted to figure out how many days I had a good sales day, and I could define what a good sales day was, what I'm going to do is I'm going to group this by each month and each location. And for each one of these groups, I'm going to figure out, for that group, do I have more than 2,500 in each one of those elements? Well, if I'm grouping by date and location, then the result is going to be each item. So this is each item over 2,500. So this means, did I sell more than 2,500 of each item on that particular, and if I group it by the day and the location, on that particular day, and I got all of them, and then I sum that up, okay. This says how many days within the month did I have a good sales day? How many days within the month did I sell more than 2,500 hamburgers and more than 2,500 French fries and more than 2,500 milkshakes? And you can see I didn't have that many great days, but maybe if I introduce some more sales, maybe some more combo deals, maybe I'll have more great days in the future. If it's the case that I want to do something more sophisticated, like I want to look at, for example, the difference in how my sales move on a year by year basis, on a month by month basis, on a day by day basis. It is incorrect for me to do a diff because you can see multiple distinct entities are stored within this data frame, and the diff is not going to separate these. In other words, this diff here is the difference between New York milkshakes on this day and New York hamburgers on that day, and that's not what you wanted to do. It is very common for nested group bys to show up in practice, especially when you have these multi-indices on your data frames, or on your series, because what you're going to do with that group by is you're first going to isolate the comparable entities, and then you're going to operate within those. I cannot compare San Francisco hamburgers against San Francisco French fries on a day-on-day difference. That doesn't make any sense. I need to look at the same thing, the same location, the same item, but just different days. And so in order to compute this, instead of using a diff, what I'll do is I'll look at the same location and the same item, and then I'll do a transform. I'll do a transform because I want this change to have the exact same shape as the input. I want it to still be the day, the location, and the item, but instead of the total amount, I want it to be the delta, And so I'll just do a diff, and I'll fill the initial values with zeros. And here, this now represents how many milkshakes I sold on this day for this location in comparison to how many milkshakes I sold on the previous day for that location. So what do we do about this? Well, when we're performing a group by or any other windowing operation, we want to pay attention to what our index looks like. It is critical that we look at the indexing because the indexing is going to help us determine what operation we want to perform. We need to look at the grouping. Well, what is the scope or scale of the operation? Are we looking at groups of months? So we're looking at groups of days together? Are we looking at groups of items together? Are we looking at groups of locations together? Are we looking at some combination of these together? And what does the result look like? Does the result look like the input in terms of the indexing? Does it look like the input? Does it look like the grouping in terms of the indexing? And based off of that, we can make a decision between aggregate and transform. In general, we want to prefer the built-in operations where possible and avoid apply where possible, but there may be cases where we can't use a built-in operation. It's not defined for the particular operation we want to do, or where we can't avoid apply. There's just not any way for us to easily express what we want to do without using apply. There's a simple table here, and you can see aggregate and transform work on individual columns. Apply works on the entire group. Aggregate and transform will change the indexing. If you're doing an aggregate, the result will have an indexing equivalent to the grouping. Transform will have an indexing of the result equivalent to the input, and you can see the broad shape of the operation. Apply, anything goes, so it is extremely flexible. It is your grab bag if you can't find some other way to fit that computation to aggregate and transform, but something that's worth avoiding if you can.